Okay, we're here talking about linear momentum. And our first example involves a rainstorm. Rain comes down with a velocity of negative 15 meters per second and hits the roof of a car. The mass of rain per second that strikes the roof of the car is 0.06 kilograms per second. Assume that the rain comes to rest upon striking the car. Find the average force exerted by the rain on the roof. Neglect the weight of the raindrop. Well, we would first start by your starting equation here. The impulse equals the change in momentum. Both of those are vectors. All right. So the impulse is equal to the net force acting on, in some moment in time, acting over some time duration, which then equals mv final squared minus mv initial squared. So we want to find the average force exerted by the rain on the roof. So F net equals, well, first of all, the raindrop comes to a stop. So VF equals 0. We see that down there. So we can just say that equals 0. And we can say the force equals mv0 squared over delta t. And that's all we have to do is plug in. Well, actually, we can group it a little bit differently. Negative m over delta t times v0 squared. And this we're given from the problem here. So force net equals negative 0.060 kilograms per second mass over time interval times the velocity in the beginning, which is negative 15 meters per second squared. When we do that calculation, we get positive 0.90 newtons, which is exactly what we'd expect because the average force is upward because it has to stop that raindrop. The raindrop's coming downward, the force is applied in the upward direction to stop it. Okay, our next example is the ice skaters. I'm sorry I didn't print this out, but initially you have ice skater 1 and ice skater 2 that are standing next to each other. That is our system. We define our system as the two ice skaters. And in the end, you have ice skater 2 going this way, ice skater 1 going this way. Again, our system is still the two ice skaters. We're given mass 1 equals 54 kilograms, mass 2 equals 88 kilograms, V final 1 equals plus 2.5 meters per second, and V final 2, we don't know what that is. And that's what we need to find. We also know in the very beginning, because the ice skaters are not moving, V01 equals V02 equals 0. Because they're not moving, they use their own force from pushing off each other, and finally they're moving in opposite directions. Now we're not talking about energy here. That's an important thing to note because they are adding energy into the system by pushing off of each other. So they're eating food, they're metabolizing that food, storing the energy, and then using the energy to make their muscles contract, pushing off each other, adding energy to the system. But we're just talking about momentum. We can ignore the energy involved there. So we know that the external force acting upon the system times the amount of time equals the change in momentum. But we also know there's no force acting outside into the system. That doesn't exist. The forces are all contained within the system. So that means P final minus P initial equals 0. I'm going to just drop the vector bars and I'm going to start talking about magnitudes. And what that means is I'm assuming everything is moving to the right here. If my assumption is wrong, our answer will come out negative. And then we'll know it's moving to the left. But I'm dropping the vector bars because I'm just using magnitudes. P final equals P initial. So in the final case, you have M1 V1 final, that's the momentum of the first person, plus M2 V2 final, that's the momentum of the second skater, equals the momentum in the beginning, which is M1 V1 initial plus M2 V2 initial. Well, what do we know about the beginning? Well, both velocities are 0, so there's no momentum in the beginning. So then we know that M1 V1 final must equal negative M2 V2 final. We are solving for this, so we'll divide each side by negative M2, and V2 final equals negative M1 V1 final over M2, which equals negative 54 kilograms times 2.5 meters per second. That's positive, and so we'd say that's in the direction to the right where we normally define positive things, positive motion. Divided by M2, which is 88 kilograms, and V2F then just equals negative 1.5 meters per second. So it's negative, so my assumption that everything is moving to the right is incorrect. So the second skater is moving to the left, which is exactly what we were told in the question prompt. Okay, so there is a running back, a 96 kilogram running back, that attempts to score a touchdown from the 1 yard line by leaping over the forward line. He is met in midair by a 105 kilogram linebacker who grabs hold of the ball carrier. That means it's an inelastic collision because they grab a hold of each other and become like one unit, one mass. When they meet, the horizontal velocity of the ball carrier is 5.22 meters per second, and the linebacker has a horizontal velocity of 4.93 meters per second in the opposite direction. Is the momentum of the running back enough to put him over the goal line? Well, let's set up our problem. I'll call this guy M1. I guess I could call him MRB or something, but that just gets kind of messy. So call the bigger linebacker M2. This is V1 initial. This is V2 initial. M1 equals 96.0 kilograms. M2 equals 105 kilograms. Let's see. V10 equals 5.22 meters per second. V20 equals 4.93 meters per second, but in the opposite direction, so I'm going to put a negative in there. So I guess this would technically need a vector bar here. All right, so the force external times delta t equals the change in momentum. We know there's no external force here because we have M1, M2 coming together, and the system is just those two football players. So that equals 0. So the momentum initially equals the momentum in the end. So M1 V1 0 plus M2 V2 0 is going to equal M1 plus M2 V final. That's because the players grab onto each other and now they're moving with the same velocity. So now what are we after here? We need to see if the momentum of the running back is enough to put him over the goal line. So basically what we need to do is we need to see that whether they end up moving forward or moving backward. So if we choose the running back to be moving in the positive direction, then V final must be positive for him to score. If V final is negative, that means the linebacker has brought him back in the other direction. So V final then is just equal to M1 V10 plus M2 V20 over M1 plus M2. Okay, so V final, and we're just dealing with magnitude, so I'm going to insert the negative. I'm going to say these two will subtract because we know that one's going to be negative. So that is 960.0 kilograms times 5.22 meters per second minus 105 kilograms times 4.93 meters per second over 96.0 kilograms plus 105 kilograms. When you calculate that out, you get negative 8.22 times 10 to the negative 2 meters per second. The running back is stopped. That is because this momentum here from the linebacker is greater than this momentum from the running back in the beginning. Remember, momentum is mass times velocity, so the bigger guy does not have to be moving as fast to have the same momentum, or in this case, just a little bit more. All right. The next problem is the ballistic pendulum. This is like the classic quintessential problem for dealing with momentum. Every physics class will talk about a ballistic pendulum. What's happening here is the mass of a block of wood is 2.5 kilograms, and the mass of a bullet is 0.01 kilograms. The block swings to a maximum height of 0.65 meters, which is over here, above the initial position. We must find the initial speed of the bullet. Okay, so we're probably going to have to do 2 steps, as I would imagine have already figured it out. So first, in part A, we define our system as the bullet and the block. So part A, we can say the external force acting in some time duration is equal to the change in momentum. There's no external force acting on the system, so we'll say the change of momentum equals 0. The change of momentum is P final. Well, we'll just say the final momentum equals the initial momentum, because change of momentum is P final minus P initial, that equals 0. I'll skip a step there and just say P final is equal to P initial. So M bullet, that's M sub little b, B little b 1, plus M capital B for the block, V capital B, I should say this is initial. No, it's final, excuse me. Talking about final velocities here, equals I screwed that up. Let's just go back a little bit. Okay, let me talk about the momentum in the initial case is M1 V, well, we'll call that M little b for the bullet, and V little b initial for the bullet, plus, or you know what, let's just call it Okay, so it's defined in the problem here as M1 and M2. So that's M1 and that's M10. That's the bullet. The block is M2 and V20. In the final case, though, the block and the bullet are together as one. See, they join together. So this is going to be M1 plus M2 V. We can just call it V final without subscript because 1 and 2 are together. Now we know in the beginning that the velocity of the second block, the M2, is 0. So we can set its momentum equal to 0. That makes things a little bit easier. And we want to find the initial speed of the bullet. Okay, so we can solve for that. V10 equals M1 plus M2 over M1 times Vf. All I did was divide each side of the equation by M1. Okay, so we have the mass of the block, the mass of the bullet, and oh no, we don't have the final velocity. So what are we going to have to do? Well, we're going to have to work the problem from a different angle. Let's see if I can zoom. No, I can't zoom out. Just move it down like this. Which is the work energy theorem. Okay? So we have this point here where the bullet and the block are moving together, and then it goes up to this point where it stops at its maximum height, which is, call that H. Call it H final. H0 equals 0. So this equals H final, and the change in is going to equal H final. Well, we can then say the work from non-conservative forces is equal to the change in energy, but there is no work from non-conservative forces here because we just have gravity acting upon this bullet block combo. So the final energy equals the initial energy. So 1/2 mv final squared plus mgh final equals 1/2 mv initial squared plus mgh initial. Well, we know in the beginning we defined this as the h0 point, so that term drops out because h0 is 0. In the end, this is the highest point that the bullet and block obtain, so its velocity must equal 0 because it's stopping there. So mgh final equals 1/2 mv initial squared. Here's where we're this is where things are going to get a little confusing because the velocity in the beginning of this scenario, the second half of the problem, that initial velocity is equal to the final velocity in part 1. So V0 from part 2, I guess I should say B, excuse me, because we've got these scenarios labeled A and B. So V0B equals V final A. So we're going to solve for V final A. You'll note that the masses cancel out of each side. I multiply each side by 2. V final A squared equals 2GH final. V final A equals the square root of 2GH final. But you may remember from A, we defined this equation, V10, and I'm going to have to call it V10 from A, because it's from the part A of the problem. M1 plus M2 over M1 times V final, which is actually V final A, from part A. And what do you know? We found that from the second part. So V10A equals M1 plus M2 over M1 times the square root of 2GHF. and you could even call it FB. You want to designate this from part B. So this equals 2.50 kilograms plus 0.0100 kilograms over M1, which is 0.0100 kilograms, times the square root of 2 times 9.8 meters per second squared. G and H is 0.650 meters. So V10A equals, got it here somewhere, 896 meters per second. All right, we have the running back. Okay, this one is a beast. You're going to hate this one. The inelastic collision problems are not tough, just long, tedious. There's a lot of math. Okay, so let's get started. Two gliders collide on an air track during a physics lab experiment. The target glider of mass this mass is at rest when struck by an incoming glider of that mass. The velocity of the target glider after the collision was measured to be this in the same direction that the first glider had before the collision. By using magnetic bumpers aligned so that the gliders repel one another but never actually touch, the collision is made to be essentially perfectly elastic. Calculate the velocity of glider A before and after the collision. Oh boy. Okay, so let's write down stuff we know. MA equals 0.189. And we have VA before, we don't know that, and we have VA final, and we don't know that either, but we want to find them. MB is equal to 0.287 kilograms. VB initial equals, well, it's at rest, so it equals 0, and VB final equals 0.250 meters per second. And we will assume in the positive x direction. Because it doesn't tell us, it just says in the same direction as this is initially. So we will assume that VA0 is positive. Well, it has to be positive because we assume this to be positive. If we assume this to be negative, then this would have to be negative. Okay, so two gliders collide on an air track. Okay, so the force external times delta t is equal to change of momentum, as always. But there's no external force acting on any of these things because it's just two objects colliding. They're isolated. They are the system. So the momentum initially is equal to the momentum in the end, final. And I can put vectors there if you want. But now I'm going to just start using magnitudes. Okay, so in the beginning, you have M-A, V-A naught. That's the initial momentum of the glider, of the glider A, plus M, B, V, B, 0, and we know that's going to be 0 because it's at rest. And in the end, you have M, A, V, A naught, and that is plus m. I'm sorry, that's final. MBVB final. Now that is plus because this should have the same sign as this. This we are going to assume is also moving in the direction to the right, but it may come out negative. We're not sure yet. Let's see. So I can write that. BAF plus MBBF. Right now, we don't know what this is. We don't know what that is. We do have this stuff, and we have the masses. So we have, we have an equation with two unknowns. So we can't do anything with that yet, but I'm going to just call that equation 1. What does a perfectly elastic equation mean? Well, elastic means that energy is conserved. If the two were to run into each other and kind of crinkle and stop or whatever, that crinkling of the material is going to absorb a lot of energy. That's why a car is made to crinkle when it's impacted, because it wants to absorb the energy of the impact. But in this case, it's completely elastic collision, so they bounce off of one another. So then we can talk about the initial energy equals the final energy. I could have started with the work non-conservative, but there's no non-conservative work going on here. So we say the energy in the beginning is equal to the energy in the end. Is there any potential energy? Well, let me just write that. KE initial plus PE initial. This is the energy of the system, remember. KE final plus PE final. Well, potential energy, we can't say that the potential energy is 0, but we can say it's the same in the beginning and the end because they're moving horizontally, so there's no gravity playing a role here. So the potential energy goes away, so we can just say that the kinetic energy of the system in the beginning, which is equal to 1/2, well, let me write it out this way. KEA plus KEB equals KE, well, these are both initial, KEA final plus KE B final. So that equals 1/2 MA VA initial squared plus 1/2 MB VB initial squared, which equals 1/2 MA V final squared plus 1/2 MB VB final squared. Okay, well, we know that this block in the beginning is 0, correct? So we just have this stuff. The 1/2 is going to cancel out from every term. So MA VA initial squared equals MA VA final final squared plus MB VB final squared. If I want to clean this up a little bit, I'll divide everything by MA. So VA initial squared equals MA over MA, cancels out. It cancels out here too. VA final squared plus MB over MA VBF squared. All right, so I'm back to an equation with two unknowns. Just say UK. So I'll give that equation a number, and I'll call it equation 2. If you remember equation 1, which was back here, I'm going to write that now down, but I'm going to divide everything by MA. I'll show you why in a second. VA initial, because MA over MA is 1, MA over MA is 1 here too, VA final, plus MB over MA, VB final. Oops, sorry, it's off the screen. So I took everything here in equation 1 and divided every term by MA, which got rid of both of these, but left MA over here. So that's what we have. So we have two equations with two unknowns. We can now solve that. We have a system of equations. Several different ways we can do it, but let's just take this and plug it right into equation 2. So that means VA0 squared equals VAF plus MB over MA VBF squared, which equals VAF squared plus MB over MA VBF squared. So I took this whole thing and plugged it in for VA naught, and then I squared it. But it's a binomial, so you can't. You have to remember how to handle this. A plus B squared. Well, first of all, it does not equal A squared plus B squared. A plus B squared equals A squared plus B squared plus 2AB. That's from the FOIL method, remember, because if you have A plus B squared equals A plus B times A plus B. So you end up with A times A is A squared, A times B times A, and then B times B, which is B squared. So you have A squared plus B squared, and then AB plus BA. Well, that's the same thing as saying 2AB. All right, so over here, that means we have VAF squared plus MB over MA VBF squared, that's A and that's B, plus 2 times VAF times MB over MA VBF. And then we'll just bring, the right side of the equation down. VAF squared plus MB over MA VBF squared. Whew, that's messy. What can we do to cancel this out? Well, we have VAF squared on each side of the equation, so luckily that goes away. Do we have anything else? Well, we have MB over MA on all sides of the equation. Here that goes away, but then this would just go to 1. So that would be MB over MA VBF squared. See, both of these things were squared, but since we have... Oh, we can't do that. All right, take it back. Okay, so I guess the best thing to start doing is group stuff together. We know we're going to go after this VAF, so we'll write 2VAF, and I'll just put it in parentheses to make it a little cleaner. MB over MA VBF equals MB over MA VBF squared, and I'm going to bring this term over, so it's positive here. I'm going to subtract it from each side, which would cancel that out, and that would give us minus MB over MA times VBF quantity squared. All right. I will actually write that a little differently. I will write that, put the parentheses over here, say that's squared and that's squared. So what would happen if I would come over here and just divide this by MB over MA VBF and divide this side over MB over MA VBF? Okay, well, that goes away. So 2VAF equals this over that. Well, these two things are going to cancel out, and this is going to cancel out one of those, so you have a VBF left minus, well, this whole thing is squared, so this would cancel out one of them, so it would just be MB over MA times VBF. Well, I can pull out the VBF and just say 1 minus MB over MA. And now I have to divide each side by 2. So VAF equals 1/2 VBF times 1 minus MB over MA. All right, so we've got the expression down as simple as we could possibly get it. So now, and everything's fine because we know everything on this side of the equation. We don't know what's on that side of the equation. So that equals 1/2 times 0.250 meters per second times 1 minus, make that into a bracket, 0.287 kilograms over 0.189 kilograms. And when you multiply all that out, you get negative 0.05648, excuse me, 648 meters per second. So that is the final velocity of cart A. Well, we have the final velocity. What is the initial? Well, that's actually a simple one to solve because all we would have to do is plug this back into one of these equations. I like the one without the squares, so let's take this down here and go all the way up to right here. I'll get a clean sheet for that. So VA naught equals VAF plus MB over MA VBF, which that equals negative 0.0648 meters per second plus 0.287 kilograms over 0.189 kilograms times 0.250 meters per second. And that means VA naught is going to equal positive 0.315 meters per second. Okay, so let's think about this for a second. This makes perfect sense, right? Because the cart is initially is going with some velocity towards MB, which is stationary. So it has a positive velocity in the beginning. VA naught is positive. Then after they hit, this is after the collision, MB is moving to the right with some velocity, and MA is moving to the left with some velocity because it's negative. Okay, that was the tough question.